Time is a one-way street. We all travel it, but we can't explain it. And that simple fact hides a secret. A cosmic secret called entropy. It's the hidden force that gives time its arrow. That shapes the fate of everything. Why does a shattered glass never piece itself back together? Why do we remember the past, but not the future? The answers are in a journey. From the steam engines of the 19th century, to the event horizons of black holes, and by the end, you'll understand the law. The fundamental law that makes yesterday different from tomorrow. That dictates the ultimate destiny of the universe. What if the flow of time isn't a fundamental feature of reality? What if it's a cosmic accident, born from a special moment at the beginning of everything? And how could the bizarre rules of the quantum world be entangled with our everyday experience of cause and effect? We're going to decode the physics. The physics that locks time into its relentless forward march. What does it mean for our reality that time can only flow in one direction? The vase is on the floor. Broken into pieces, sharp pieces scattered, and no one standing there waiting for it to come back together. We just know it won't. We feel that it's a deep feeling. And that feeling is our closest touch with something cosmic, the arrow of time. It's this undeniable sense that yesterday is gone. The future isn't written yet. Things happen in a sequence, and that sequence doesn't run backward. We remember breakfast. We don't remember tomorrow's lunch. That's the psychological arrow. Our consciousness flowing from memory into anticipation. It points one way, and there's a cosmological arrow too. The universe is expanding. It started dense and hot, and it's moving into some future. All these arrows line up. They paint the same picture. A universe moving from a definite past toward an open future. But why? If you filmed two atoms colliding and played it backward, it would look normal. The fundamental laws of physics, they don't care about time's direction. They're symmetric. So where does this bias come from? This overwhelming bias in our reality? In the early 20th century, an astronomer and physicist, Arthur Eddington, gave it a name. He said among all the arrows, one was primary, a master arrow. The one all the others follow. That's the thermodynamic arrow, governed by one powerful concept, entropy. It's the hidden fingerprint on every event that can't be undone. It's why the vase stays broken. It's the secret force that gives time its direction. To understand time, you have to understand this disorder. The story of entropy starts with a man in a quiet study. Ludwig Boltzmann, an Austrian physicist, he had a radical idea. He said the warmth of your coffee, the pressure of the air, these weren't fundamental things. They were illusions, stories told by atoms, countless atoms in motion. His insight was about entropy, this tendency toward disorder. He said it wasn't a force. It was a statistic, a numbers game. To see it, you have to think about disorder differently. Not a messy room, think about possibilities. Take a deck of cards fresh from the box. It's in perfect order. That specific arrangement is incredibly rare. Just one possibility, among an astronomically large number of ways you could shuffle that deck. If you toss the cards in the air, the chance they land in that same order is virtually zero. They'll land in some other configuration. That random state isn't more disordered, it's just more probable. There are far more ways for the deck to be shuffled than to be ordered. Boltzmann applied this to the universe, a box of gas. To our eyes, it looks uniform. A calm cloud, but at the atomic level, it's a chaotic storm. Each molecule has a position and a speed. What we measure is a macrostate, the gas evenly filling the box. A microstate is one specific snapshot, where every single molecule is and how it's moving. The key is that a single, simple macrostate, like gas spread out, can be achieved by a nearly infinite number of microstates. The molecules can be arranged in countless ways and still look uniform to us. But the macrostate of all the gas crammed into one corner, that corresponds to a very small number of microstates. A very specific, very unlikely arrangement. This was his genius. He gave it a form. He said entropy S equals a constant K. times the logarithm of W, where W is the number of microstates for a given macrostate. S equals K log W. That equation is a bridge. It connects the invisible world of atoms to the world we experience. High entropy means a macrostate with a huge number of possible microscopic arrangements. And because those arrangements are so numerous, they are overwhelmingly more probable. So the gas spreads out in the room, it's not being pulled, it's not seeking disorder, it's just wandering statistically into the vastly more probable state, where its molecules are everywhere, not bunched up. A broken vase has high entropy because there are astronomically more ways for its pieces to be on the floor than ways for them to be an intact vase. The universe started in a highly ordered, low-entropy state at the Big Bang. It's exploring the statistical possibilities, moving toward the more probable states. And that statistical drift, from less probable arrangements to more probable ones, is what we feel as the flow of time. Boltzmann's work faced fierce opposition from scientists who believed in a continuous reality, not a statistical one. The personal toll was profound. His story ended in a way that reminds you how deeply the search for truth can affect someone. But his legacy transformed physics. He gave us the language to ask the next question. If it's all about probability, what is the law that makes the probable seem inevitable? Boltzmann gave us the language for it, but the rule itself that came from steam, from engines, the Industrial Revolution. They were trying to get more work from coal, from fire. And they found this limit. In every machine, some energy was lost, wasted as heat. You couldn't get it back. That observation became the second law of thermodynamics. It has different forms, but they all say the same thing. Rudolf Clausius had a simple way to put it. Heat doesn't flow on its own from a cold thing to a hot thing. Your ice cube melts in your drink. The room's warmth flows into the ice, it doesn't go the other way. To reverse that, you need a refrigerator, and that takes work, which makes more heat somewhere else. It's a one-way street. Lord Kelvin saw it another way. You can't have a process where the only result is heat turning completely into work. You can't have a perfect engine. There's always a tax. A dispersal, these aren't different rules, they're just windows looking at the same truth. The total entropy of an isolated system always increases. It never goes down. Remember Boltzmann's equation? Entropy is the count of microscopic arrangements. The second law says the universe moves, statistically, from less probable arrangements to more probable ones. From order to disorder, not because it wants to, but because disorder has more ways to be. This is what drives time. Sean Carroll has a good way to say it. The second law is why you can't unscramble an egg. Think about that. Scrambling an egg is easy. You add energy, you disrupt the order. It becomes a uniform mixture. A high-entropy state. To unscramble it, you'd have to guide every protein molecule, every bit of yolk and white, back to its original place. You'd have to reverse the motion of countless particles. It's so improbable, it might as well be impossible. The scramble is a one-way trip. That's the reality. Every process pays this tax, a star burning its fuel. A leaf decaying. Energy disperses, things mix. The universe becomes statistically more uniform. This irreversible move from lower entropy to higher entropy, that's what we feel as the flow of time. It gives time its arrow, a preferred direction. But this leads to a big question. If the second law pushes things toward disorder to drive time forward, then the universe must have started with extraordinary order. Incredibly low entropy. Why was it like that? What set the clock ticking with the spring wound so tight? The answer to time's arrow might not be in the law itself. It might be in that unique, mysterious starting condition, the one from which everything expanded. The universe started with a kind of order. It was this hot, dense plasma, incredibly uniform. When we look at the afterglow of the Big Bang, the cosmic microwave background, it's almost perfectly the same in every direction. To us, that looks like chaos, a fireball. But in terms of probability, it was a state of very low entropy. Like a deck of cards right out of the box, all in sequence. All the matter and energy packed into a tiny volume, but smoothed out in a way that's statistically very rare. That's the puzzle. Why did it start in such a special, improbable state? Philosophers of science, David Albert for one, they call this the past hypothesis. It's the proposed boundary condition the universe began with low entropy. And this fact is the reason for everything we experience. It's the wound-up spring that drives time. Without that starting point, the second law of thermodynamics wouldn't give us an arrow. In an eternal, fluctuating universe, entropy would go up and down. You might see a broken vase reassemble itself as often as it shatters. Memories could form of the future just like the past. There'd be no master direction, just statistical noise. Our consistent experience of time from past to future, it all depends on that one event at the beginning, so we're left with the mystery. What physical principle set the stage this way? Was it just a brute fact, an initial condition with no deeper explanation? Or does the answer lie before the Big Bang, in the laws that brought the universe into being? This mystery ties the fate of time directly to the origins of everything. That unique starting condition gave us more than a wound-up spring. It gave us a stage. An expanding stage. The universe didn't just cool from that hot beginning, it stretched. Space itself has been growing for billions of years, carrying galaxies along like raisins in rising bread. That expansion is the cosmological arrow of time we see. And it's deeply tied to entropy, but in a way that flips our everyday intuition. For a gas in a box, the high entropy state is uniform. Spread out. For gravity, the rules are reversed. Gravity loves clumps. A perfectly smooth, uniform cloud of matter spread thin across the cosmos, that's actually a state of incredibly low gravitational entropy. It's too orderly, too simple. Gravity wants to amplify tiny imperfections, to pull matter together, to build things, stars, galaxies, clusters. These complex structures are actually the high entropy state for gravity. They represent a vastly larger number of ways for matter to be arranged when you account for the pull of spacetime itself. The expansion of the universe is what makes this possible. It's the engine that lets gravitational entropy rise. Think of it this way. If the universe were static and uniform, gravity would pull everything into one giant clump. It would happen fast, and then it would be over. But the expansion stretches the stage while the play is happening. It gives gravity time and room to work. It lets small density ripples in the early universe become seeds. Over eons, gravity sculpts those seeds into the vast cosmic web we see, a web of galaxies and voids. That process, creating structure from smoothness, is a massive increase in gravitational entropy. This perspective, from physicists like Roger Penrose, reshapes our view of the cosmic end. The traditional heat death imagines a cold, dark, uniform universe where everything is perfectly mixed and nothing happens. But if clumps are high entropy for gravity, then the ultimate high entropy state might look very different. It could be a universe dominated by the ultimate gravitational sinks. Black holes. They're not just cosmic vacuum cleaners. In this view, they're entropy factories. A black hole's event horizon hides a staggering number of microscopic states, a phenomenal amount of entropy locked away from the rest of the universe. So the final act might not be a featureless sea. It might be a dark, quiet cosmos scattered with these profound monuments to gravity's work, having reached its maximum possible disorder. So the expansion of space is far more than galaxies flying apart. It is the essential arena, the unfolding canvas, that allows the universe's total entropy from matter and from gravity to steadily increase. It weaves the cosmological arrow directly into the fabric of space-time, giving the direction and the space for time's arrow to point. But this raises a profound question. If black holes are the pinnacle of gravitational entropy, what happens to all that information, all that complexity, swallowed by their immense gravity? The answer to that may lie in the most surprising of places, at the bizarre boundary where gravity meets the quantum world. a film reel of billiard balls colliding. Play it forward, you see the break. The crack, the balls scattering, now play it backward. The chaotic dance reverses. Balls come careening from the cushions, gathering, arranging themselves back into a perfect triangle. The cue ball rolls back and jumps onto the tip of the cue. It looks wrong, impossible, but the puzzle is, the laws of physics say that backward film is just as valid. Newton's laws, the equations for each collision, they're time-symmetric. They don't have an arrow. If you know the positions and velocities, the laws work equally well predicting the past or the future. The microscopic dance is reversible. So why does the reversed sequence feel impossible? Why do we never walk into a pool hall and see scattered balls snap back into a triangle? That's the heart of it. The bedrock laws, from classical mechanics to Schrödinger's equation, show no preference for past or future. They are ambivalent. Yet our world is full of irreversible things. Smoke never pours back into a cigarette. Spilled milk never leaps back into the glass. This chasm between reversible laws and irreversible reality, that's where time's arrow is revealed. The answer isn't in the laws. It's in the starting conditions, and it's in statistics. Think of the deck of cards. An ordered sequence is one possibility among a vast number of shuffled possibilities. The billiard balls in a triangle, that's like the ordered deck. A specific, low-entropy arrangement. When the break happens, the system explodes into a high-entropy state. Countless ways for the balls to be scattered, but for them to spontaneously find the one precise set of paths back into the triangle. The odds are so vanishingly small they might as well be zero. The laws don't forbid it. The laws would allow it if every molecule of air, every vibration, every microscopic bump aligned in a perfect, conspiratorial sequence to guide each ball home. But that coordinated sequence is just one microstate. The scattered balls represent a near infinity of microstates. The system, left to its own statistical wanderings, will almost certainly be found in one of the vastly more numerous disordered states. That resolves the contradiction. Microscopic reversibility is a property of the individual paths, the specific dances of particles. Macroscopic irreversibility is a property of the crowd. It's the difference between one person walking backward and an entire stadium spontaneously marching in perfect reverse synchronization. One is allowed by the rules. The other is so statistically improbable we never expect to see it. So time's arrow emerges not from the laws, but from the journey from improbable order to probable disorder. The irreversible world we experience is the statistical certainty of the crowd, written large. Our past, our present, our future. They are the narrative woven by this relentless statistical drift. And that brings us to an edge. If our experience of time is born from statistics and a special beginning, what does that mean for the very end? When the universe has explored nearly all its possible states, when entropy approaches its maximum, what happens to the arrow then? Does time begin to fade? The universe started with a wound-up spring. That low-entropy beginning is what set time's arrow in motion, but that raises a question. Why, what condition, what law, could have put the early cosmos in such a finely tuned state? High entropy is normal, so our start was astronomically special. It's like shuffling a deck once and getting perfect order. Possible, but staggeringly unlikely. So what stacked the deck? One idea is cosmic inflation. A fraction of a second after the beginning, a patch of space went through hyper-fast expansion. A tiny, maybe chaotic region stretched to an unimaginable size. This process, driven by a peculiar energy, would have ironed out wrinkles, smoothed temperature and density. It delivered the uniform, low-entropy condition we see in the cosmic microwave background. In that view, the arrow of time is a consequence of that smoothing. Our ordered beginning wasn't the absolute start. It was the result of a dramatic event that reset the cosmic clock. Another idea is the multiverse. Our universe might be one bubble in a vast, eternal foam. In that landscape, most regions are high-entropy messes, timeless. Formless, but through sheer chance, through infinite random fluctuations, a rare bubble like ours can pop into existence with the right low entropy conditions. We find ourselves here not because it's likely, but because it's the only kind of place where beings like us could ever arise to ask the question. Our entire cosmic history becomes a rare statistical fluctuation within a much larger, disordered meta-reality that makes the arrow of time a local accident, a lucky draw. But this leads to a troubling paradox, one that haunted Boltzmann himself. It's called the Boltzmann brain. If our universe is just a random, low-entropy fluctuation in an eternal sea of disorder, then what's the most probable way for a conscious entity to appear? The answer is unsettling. It would be far more likely for a single, self-aware brain to spontaneously form from the chaos, complete with false memories of a past and a universe, than for an entire ordered cosmos spanning billions of light years to fluctuate into existence. You, listening right now, would statistically be more likely to be that momentary, disembodied illusion, a brain floating in the void, than a person in a real, evolving universe. This isn't just a strange thought experiment. It's a serious philosophical challenge to any explanation relying on random chance. It suggests that if our beginning was a mere fluke, then our own conscious experience should be untrustworthy. The fact that we observe a vast, consistent, law-abiding cosmos rather than a fleeting hallucination is a powerful clue. Something is wrong with that picture. It pushes us toward a different conclusion, that a deeper principle must have guided the initial conditions, making an ordered universe not a freak accident, but an expected outcome. So the origin of time's arrow pushes physics to its limits. It asks whether our flowing present is rooted in a cosmic accident, or if it emerges from a fundamental law we have yet to grasp. This mystery forces us to look not just at the beginning, but at the fabric of reality. And to solve it, we might need to go to the most extreme environment the universe has to offer. A place where time itself behaves in ways that defy intuition. A place where the arrow of time might not just flow, but where it could, theoretically, be broken. Black holes are gravity at its most extreme, a place where spacetime curves so much that inside the event horizon, the escape velocity is faster than light. So nothing gets out, not even information. For a long time they were just considered dead ends, the final resting place for matter and light. But then, in the 70s, Jacob Bekenstein made a connection. He thought, if you throw something with entropy into a black hole like a hot cup of coffee, the total entropy of the universe would seem to go down. That would break the second law. Unless the black hole itself had entropy, and that this entropy was tied to the area of its event horizon, not its volume, it was a radical idea. Entropy, which is disorder linked to a surface area. Stephen Hawking didn't like it at first, but his own work led him somewhere shocking. He showed black holes aren't completely black. Quantum effects near the horizon mean they should glow with a faint radiation. Hawking radiation, and that radiation meant black holes have a temperature. And if they have a temperature, they must have entropy. So the Bekenstein-Hawking formula says the entropy is 1/4 the area of the event horizon in Planck units. It's a huge number. A single stellar black hole holds more entropy than all the particles in the visible universe. That linked three things: thermodynamics, gravity, and quantum mechanics. It suggested the information about what falls in isn't stored in the volume, but on the two-dimensional surface, like a hologram, but that created a paradox. Hawking radiation is thermal. It's random noise like static from something hot. It doesn't carry specific information about what fell in, so take a book. You throw it in. The book has information, the arrangement of its atoms, the words on the page. Quantum mechanics says information is never destroyed. It can be scrambled, but it must be recoverable in principle. If the black hole evaporates through Hawking radiation, leaving only that thermal glow, then the book's information is gone forever. That's the black hole information paradox. It means something's wrong. Either quantum mechanics is wrong, or our understanding of gravity and black holes is incomplete. This isn't a small detail. It questions whether the universe is predictable. If information can vanish, the past isn't a fixed record. Cause and effect break down. The arrow of time, which needs a consistent flow from past to future, loses its footing. Solving this is seen as a key step toward quantum gravity. Current ideas, like the holographic principle, say the information isn't lost. It's preserved on the event horizon and slowly encoded into the radiation, in a way so complex it looks random to us. In that view, the black hole is the most efficient information processor there is. It changes how we see them. They're not just destroyers. They're entropy engines, and maybe the keepers of time's deepest secret. If the fate of information at a black hole's edge holds the key to unifying quantum mechanics and gravity, then it might also tell us why time has a direction. But to find that answer, you have to go somewhere even stranger, where the rules of cause and effect are tested. Your first memory is something your brain wrote. The smell of rain on hot pavement, or grass under your feet, or a parent's voice. That moment is gone, but your mind can rebuild it, not perfectly but vividly. It feels like a record. You can't remember tomorrow, though. You can imagine tomorrow, you can plan for it, but you don't recall it as a fact. That's the psychological arrow of time. It feels personal, internal, but it's governed by the same rule that breaks vases, that scatters billiard balls. To remember, your brain has to change. A memory forms when neurons fire in a pattern, strengthening some connections, weakening others. That's a physical process. Molecules move, ions flow. Energy gets used and heat gets dissipated. And with each of those tiny actions, the entropy of the system, your brain and its surroundings, increases. Recording a memory is thermodynamically irreversible. It leaves a trail of increased disorder. Your memory of that childhood moment exists because your brain was in a more ordered state before it formed, and a less ordered state after. Your psychological arrow is locked with the thermodynamic arrow. You remember the past because the past is the direction of lower entropy. Some thinkers go further. The physicist Carlo Rovelli, for instance, he suggests time as we feel it flowing might not be fundamental. It could be emergent. A story our brains tell because we're limited. We can't perceive the universe in full microscopic detail. We see only the big, blurry picture, the macrostate, and from that blurred view, from not seeing every particle, we infer a sequence. A before and an after. So our consciousness isn't a clock ticking in universal time. It's a thermodynamic process, a constant updating of our internal model, always oriented toward the future of higher entropy. Which leads to a dizzying question. If, by some miracle, the entropy of a system started to decrease, would consciousness run backward? Imagine a universe rewinding. Would beings in it remember the future and anticipate the past? It feels like a paradox from a dream. But logically, if their brains were part of that reversing system, their neural processes would reverse too. The strengthening of a synapse would become a weakening. The feeling of recalling a memory would become the feeling of forgetting one. Their psychological arrow would flip, aligned with their thermodynamic arrow. To them, it would feel normal. Their past would be our future. This isn't a claim about reality, it's a thought experiment. It ties our deepest sense of self to the impersonal laws of physics. It shows we're not just observers of time's arrow. We are manifestations of it. Our very thoughts are currents in that river, flowing from order to disorder. Even cause and effect start to blur. That's the quantum world. A particle isn't just here or there. It can be in a superposition, both here and there at the same time. Like a coin spinning in the air, it's both heads and tails while it spins. That's not a lack of knowledge. It's the actual description of reality before you look. But when you measure it, when you see which side is up, that superposition vanishes. The coin lands, it's heads. That's the measurement problem, the collapse of the wave function. And it's irreversible. You can't take that definite outcome and put the particle back into its fuzzy state. Measurement creates a record, a fact in the world. That process increases entropy. Information is extracted. The quantum system becomes entangled with its environment, leaving a trail of disorder. So the arrow of time might be baked into observation itself. Some interpretations try to avoid this collapse. The many worlds interpretation. It says the coin never lands on just one side. The universe splits. In one branch you see heads. In another, tails. Both outcomes occur in separate realities. There's no collapse, just an ever-branching tree. But if that's true, why do we experience only one branch? Why one timeline? The answer might be entropy again, through a process called decoherence. When a quantum system interacts with its environment, a stray photon, an air molecule, that interaction entangles the system with the environment. It's like the spinning coin being jostled by wind. That interaction chooses a branch for us, not by magic, but by making the other branches inaccessible. The information about the other possibilities leaks out. It gets scrambled. Decoherence increases entropy. It turns quantum possibility into classical certainty from our point of view. And it flows in one direction, aligning with time's arrow. This connection deepens with quantum entanglement. Two particles can be linked, entangled. Measuring one instantly tells you the state of the other, no matter the distance. This spooky action at a distance. It seems to defy cause and effect. But even here, time's arrow appears. You can't use entanglement to send a message backward in time. The sequence of measurements matters. The propagation of entanglement correlations respects the causal order defined by increasing entropy. Some physicists, like Seth Lloyd, propose the arrow of time might emerge from how quantum entanglement spreads through a system, creating the web of correlations we see as the past leading to the present. So the quantum realm isn't a separate story. It's woven into the mystery of time, the irreversible act of measurement, the branching of worlds filtered by decoherence, the one-way flow of entanglement. These quantum processes are thermodynamic processes at heart. They generate entropy, they create records, they distinguish a before from an after. That suggests the foundations of reality, the rules at the smallest scales, aren't time-symmetric like we once thought. They contain a subtle bias, a whisper of direction. That amplifies into the roar of time's arrow in our world. We're just beginning to grasp how deeply entropy and quantum mechanics are intertwined. The ultimate explanation for why time flows might be found in the quantum structure of spacetime itself. The second law seems absolute, but physics pushes at its edges. It asks whether time's arrow could ever point the other way, whether a system, under the right conditions, might see entropy drop and time effectively run backwards. The first real challenge came from James Clerk Maxwell. He imagined a tiny, intelligent creature, a demon. This demon guards a door between two chambers of gas. When a fast molecule comes from the left, it opens the door to let it into the right chamber. When a slow one comes from the right, it lets it into the left. The demon doesn't use energy to push the molecules. It just uses information. Over time, one chamber gets hot, the other cold. Heat flows from cold to hot without any work being done. The entropy of the system decreases. It looks like the second law is broken. For over a century, this puzzle haunted thermodynamics. The resolution came from an unexpected place. Information theory. The demon isn't free. To decide which molecule is fast or slow, it has to make a measurement. It has to gather information. And to store that information, even in its mind, requires a physical system. A memory, and erasing that memory to make room for new observations, is an irreversible process. It increases entropy. When you account for the entropy generated in the demon's own brain, the total entropy of the combined system still goes up. The second law stands reinforced. Information isn't abstract, it's physical, and it has a thermodynamic cost. But what about nature itself without any demon? In very small systems with only a few molecules, you can see entropy fluctuate. A tiny pocket of air might spontaneously have all its fast molecules on one side for a brief moment. It's not a violation, it's a statistical blip. In a vast universe with countless particles, Such a blip across an entire room is so improbable it will never happen. But in a microscopic volume it can and does. These are temporary, fleeting decreases in entropy. They don't reverse time's arrow, but they show its statistical nature. The arrow is a property of the crowd, not of every individual. This leads to the grandest speculation. Could the entire universe see a reversal? In some cosmological models, like a hypothetical Big Crunch where expansion stops and everything collapses back, could entropy reset? Or in a cyclic universe, bouncing from one phase to the next, could each new cycle begin with low entropy again? The answers are deeply uncertain. Most physicists think a collapsing universe would be a state of even higher entropy, a chaotic mess of colliding black holes. A true reset seems to require new physics, a mechanism to smooth and order the cosmos anew. These ideas live at the frontier. They challenge whether the arrow of time is an absolute feature of reality, or just a contingent property of our particular cosmic epoch. A phase the universe is going through. If so, then in some other realm or at some other time, the relentless flow from past to future might not be the rule. Cause and effect could unwind. Memories could form of what to us is the future. It's a dizzying thought. It stretches the imagination. It reminds us that our experience of time, so fundamental to being, might be a local condition. A story written by the particular statistics of our cosmic starting point. And that opens a door to a final, profound layer of the mystery. If time's arrow is not absolute, then what is the true nature of the present moment? And could our understanding of it be completely wrong? Erasing a memory has a cost, a real physical cost. When you delete a file on a computer, the ones and zeros don't just disappear. To reset a bit from a 1 to a 0, the system has to release a tiny amount of heat. That's not an engineering problem, it's a law of physics. Rolf Landauer discovered it. Information is physical. It's not abstract. It's always stored in something. The magnetization of a hard drive, the charge in a transistor, ink on a page. Changing that thing, erasing a bit, is irreversible. It increases the entropy of the universe. Landauer's principle says erasing one bit must release at least a specific, tiny amount of heat. It's the thermodynamic price of forgetting, and that links the digital world to time's arrow. Every computation, every logical operation, involves erasing some information to make room for new results. So every calculation, your phone adding numbers, a supercomputer simulating a galaxy is a thermodynamic process. It generates heat. It increases entropy. It contributes in its own tiny way to the universe's drift toward disorder. The flow of information and the flow of time aren't separate. They're two sides of the same coin. The computer on your desk and the conscious mind using it are both engines. They run on the fuel of low entropy. They produce the exhaust of higher entropy with every thought, with every calculation. This gives us a way to measure order. Think about describing something. A perfectly ordered sequence like a million zeros is easy to describe. You just say, a million zeros. The description is short. The information content is low. Now describe the static on a detuned TV screen. To specify every random pixel, you'd need a description as long as the screen's data itself. There's no shortcut. That's called algorithmic information complexity. The more ordered something is, the shorter the computer program needed to generate it. The more disordered, the longer the program must be. The initial low entropy state of the universe was, in this sense, highly compressible. It could be described by simple laws and initial conditions. As the universe evolves into its high entropy future, the description of its precise state becomes longer, filled with accidental details, statistical noise. Time's arrow, then, is the arrow of increasing algorithmic complexity. It's the universe generating its own longest, most intricate story from a simple beginning. So there's this connection. Consciousness, which forms memories, processes information, computation, which manipulates symbols under physical laws, and cosmology, the grand story of the expanding universe. They are all bound together by thermodynamics. Our minds aren't just observers of time's arrow, they are participants. Each thought, each memory formed and later forgotten, is a local act of increasing entropy. A stitch in the temporal tapestry. The universe computes its own future state, and the heat generated in that vast, distributed calculation is what we experience as the forward march of time. To understand time, we have to understand information, not as a mathematical idea, but as a physical substance, something with weight in the cosmic balance. A deterministic universe is a clockwork. You know the position and velocity of every particle, and the laws of physics should let you calculate the entire future. Or rewind the entire past. It suggests a world without novelty, where every event is locked in place by what came before. But our lives don't feel like that. We face uncertainty, we make choices, the future feels open, so how can both be true? The bridge is built from chaos. The classic image is the butterfly effect. A butterfly flaps its wings in Brazil, and through a chain of impossibly complex interactions, it sets in motion events that weeks later influence a hurricane over the Atlantic. It's not that butterflies cause hurricanes. It's a metaphor for a mathematical truth. In chaotic systems, the tiniest, most immeasurable difference in the starting conditions leads to a wildly different outcome. The flap of a wing is that immeasurable puff of air. A system is chaotic when it shows this sensitive dependence. The equations for the weather are deterministic. There's no randomness in fluid dynamics or thermodynamics, but the system is so sensitive that any error in our measurement, no matter how small, grows exponentially. It doubles and doubles again until predictions become useless. Within days, the forecast dissolves. The future becomes, for all practical purposes, unpredictable. Not because the laws are random, but because we can never know the present with infinite precision. This links directly to time's arrow. Think of trying to run the clock backward. You see the hurricane, you have today's data. Could you use the laws to rewind the storm, trace it back, and identify that specific butterfly weeks ago? In theory, the deterministic laws allow it. In practice, it's impossible. The reason is chaos. To rewind perfectly, you would need to know the exact state of every molecule right now with perfect accuracy. But you can't. Any uncertainty, any rounding error, gets amplified exponentially as you rewind. Your reconstruction of the past spirals into nonsense. You cannot reliably trace the path backward. So while the microscopic laws are time-symmetric, the behavior of the chaotic system is effectively irreversible. It creates a practical arrow of time. The past becomes a story we can infer only probabilistically, not a state we can reconstruct with certainty. Chaos is an engine for increasing entropy. Take our solar system. It seems stable. We can calculate eclipses thousands of years in advance, but the gravitational dance of many bodies is chaotic. We can't precisely calculate the orbits of all the planets over billions of years. Tiny perturbations, the tug of a passing star, the drift of asteroids will, over immense timescales, amplify. The orderly arrangement we see today will eventually dissolve. Planets could be ejected or collide. Chaos drives the system from predictable order toward unpredictable, higher entropy disorder. It's not creating entropy from nothing. It's efficiently dispersing the energy stored in those neat orbits, scrambling it into a form that is maximally difficult to untangle. So chaos weaves the texture of our lives. It explains why, in a universe governed by precise laws, we experience novelty and surprise. It tells us that determinism and an open future are not opposites. They are different levels of description. At the fundamental, microscopic level, the path may be set. But at the level of human experience, the level of weather, ecosystems, hearts, and minds, the future is truly unknown. Our inability to know the present perfectly, thanks to chaos, makes the future a realm of possibility. This practical irreversibility reinforces the thermodynamic arrow, making the forward direction of time an inescapable feature. It blends the cold equations with the warm, uncertain story of existence. And it leads to a final question. If chaos, thermodynamics, and quantum mechanics all point time in one direction, what does that tell us about reality? Is time's arrow a fundamental ingredient, or is it, as some now suggest, nothing more than a persistent and convincing illusion? A seed is a tiny, ordered world. It has the instructions to become a tree, a whole network of roots and branches. Life in all its forms looks like a rebellion. It builds complex things from simple parts. It makes information, purpose, beauty from chaos. So how does that work? How can living systems create so much local order in a universe that's sliding toward disorder? The answer is that life doesn't defy the arrow of time. It's actually an expression of it. Living things aren't closed off. They're open systems. They're constantly exchanging energy and matter with what's around them. And for an open system, the rule is different. It can maintain its internal order, even increase it, but only by sending a greater amount of disorder out into its environment. Take your own body. You're a marvel of organization, trillions of cells working together. But to keep that order, you have to eat. You take in chemical energy stored in orderly molecules, sugars, and fats. Your body breaks them down through respiration. You extract useful energy to power your cells, but in doing that, you convert those orderly molecules into simpler, more disordered waste. Carbon dioxide, water, and you release heat. A lot of heat. That heat is the ultimate export of disorder. It radiates from your skin, warming the air, increasing the random motion of molecules out there. The entropy of your body might stay roughly constant, but the total entropy of you plus your surroundings goes up dramatically. That's the transaction. Life pays for its local order by increasing global disorder. The most elegant example is the foundation of almost all life: photosynthesis. A leaf is a solar-powered entropy machine. It captures highly ordered, low-entropy energy from the sun. Sunlight isn't just energy. It's energy with a low-entropy signature, a concentrated form that can do work. The leaf uses this energy to do something remarkable. It takes disordered carbon dioxide from the air and disordered water from the soil and assembles them into highly ordered glucose, a sugar molecule. It creates chemical order from atmospheric chaos, but the process isn't perfect. It can't be. For every bit of order stored in that sugar, a greater amount of disorder is made. A big part of the solar energy is immediately turned into heat, which radiates away. The leaf exports entropy as waste heat to cool itself, just like your body does. When an animal eats that plant later and breaks down the glucose, even more heat is released. The original low-entropy sunlight is gradually degraded, step by step, into the diffuse warmth of the planet. The whole biosphere is a vast engine for increasing the universe's total entropy. It channels the sun's low-entropy radiation through living networks, extracting pockets of temporary order along the way, and finally releases high-entropy heat back into space. The physicist Erwin Schrödinger captured this idea. In his book What is Life, he argued that a living organism avoids decay, avoids death, by continually sucking orderliness from its environment. He called it negative entropy. Life feeds on it. It sustains its internal order by drawing from the ordered energy in sunlight or food, and in that process, it speeds up the universe's journey toward equilibrium. So the arrow of time isn't just a background feature for life. It's the driving force. The relentless increase in entropy creates the gradients, the differences in energy and concentration, that life uses to power itself. It's the reason evolution has a direction, moving toward greater complexity, as organisms find new ways to harness energy flows. And in the very long run, it's this process that led to observers. Beings complex enough to build models of the world, to form memories, to ask questions, to look at a broken vase and wonder why it never mends itself. To look at the stars and think about the one-way flow of everything. We aren't just products of time's arrow. We are its most intricate consequence. Our very ability to question time comes from time's irreversible march. The sun won't shine forever. Stars are engines. They turn mass into light and heat. But they have a finite amount of fuel. Across the cosmos, over timescales that are just unimaginably long, the lights will go out. The massive stars go first in supernova. Then stars like our Sun. They swell into red giants, then fade into white dwarfs. The smallest stars, the red dwarfs, they'll glow for trillions of years. But eventually they cool, they darken. What's left is a graveyard, stellar remnants scattered in an expanding void. That's the beginning of the end state. It's the trajectory set by the second law. But it doesn't stop with dark stars. Even the most stable structures decay. White dwarfs, neutron stars. Over periods we can't really grasp, they'll cool into black cinders. And black holes, they aren't eternal. Through Hawking radiation, they leak their mass away. A stellar black hole might take many times the current age of the universe to evaporate. The supermassive ones take almost unimaginably longer, but given enough time they fade. They shrink, grow hotter, and in a final burst, they vanish. What remains is a cosmos that's reached maximum entropy. The heat death, it's not a state of fire, it's absolute cold, not activity but perfect stillness. The universe becomes a thin, uniform sea. Fundamental particles and radiation stretched across an incomprehensible volume. Every temperature is the same. No hot spots, no cold spots. No hills, no valleys, no energy gradients left to use. In that state, no work can be done. No process can occur because a process needs a difference, a flow from higher energy to lower. And there's nowhere to flow. It's the ultimate equilibrium. For all practical purposes, the cosmos is frozen. That presents a puzzle for time itself. Our entire experience of time's arrow. Memory, causation, it's tied to the increase of entropy. It's the drive from low entropy to high. But what happens when entropy can't increase anymore? When it's at its maximum possible value? In that perfect uniformity, the concept of before and after it might lose its grip. With no processes to mark the passage, no changes to sequence, does time just stop? Or does it become a meaningless coordinate, like a longitude line on a featureless ocean? Some physicists think in that state, time would lose its directional quality. The arrow would vanish, because there's no statistical journey left to take. The universe would be in its most probable state, and it would just stay there. Forever, that seems like a final, silent conclusion, but is it truly the end? Quantum mechanics whispers a possibility, a faint echo of rebirth. Even in a perfect vacuum at absolute zero, quantum fields aren't perfectly still. They undergo tiny, random fluctuations. Virtual particles pop in and out of existence. In an eternally expanding universe nearing heat death, over scales of time that make the current age seem like a blink, one of these quantum fluctuations could be enormous. Not just a particle pair, but a fluctuation that spawns an entire new region of spacetime, with low entropy, a new Big Bang, through a process called quantum tunneling. It would be astronomically unlikely, but given infinite time, the improbable becomes inevitable. Our entire universe, its billions of galaxies, its arrow of time, it could be the result of a fluctuation in a long-dead parent cosmos. And the cycle could repeat without end. This idea of cosmic recycling offers a strange comfort. It suggests heat death may not be a full stop, but a comma. A long, dark winter before a new spring. It implies that time's arrow, our arrow, might be a local phenomenon, reignited with each new cosmic cycle. Our flowing present, our memories and hopes, they'd be part of a much longer story. Perhaps an eternal story of fluctuation and decay. This mystery forces a humbling perspective. Our understanding of time, of cause and effect, of history and future. It's built entirely within a universe that's still far from equilibrium. We are creatures of the gradient, living in the brief cosmic dawn between a low entropy beginning and a high entropy end. The laws we've discovered, including the second law that gives time its direction, they describe this middle chapter. They may not be the final word on eternity. To confront the heat death is to see our moment of consciousness for what it is, a fleeting spark of order in the vast dark. Yet it's a spark capable of understanding the dark. And in that understanding, we find a connection to the cosmos that's deeper than permanence. We are not just passengers of time. We are the universe's way of experiencing its own one-way journey. The laws of physics really like symmetry. There's a big one, CPT symmetry. It's three things together. C is charge conjugation. You flip the charge of every particle, so matter becomes antimatter. P is parity. You make a mirror image of space, swap left and right. T is time reversal. You run the clock backward. The idea is if you take any process and do all three at once, reverse charge, mirror it, and reverse time, the laws of physics should allow it. It would look just as natural. This symmetry is fundamental, a cornerstone. It means the universe at its core doesn't distinguish between matter and antimatter, left and right, past and future. But our reality isn't like that. We're made of matter. Our bodies have a handedness like DNA. Time flows one way, so if CPT is perfectly symmetric and our world isn't, then the asymmetry had to come from how things started. A broken symmetry in the initial conditions. Then physicists found a crack, a small one. It's called CP violation, charge parity violation. In certain particle decays with kaons and B mesons, they saw the process and its mirror antimatter version don't happen at exactly the same rate. There's a tiny, measurable difference. The universe shows a preference. It can tell left from right, matter from antimatter. This is huge, because if CP is violated, then by the rule of CPT symmetry, time reversal symmetry must also be violated. To keep the overall balance, there must be processes that look different forward and backward in time. This CP violation might explain a major mystery. Why is the universe almost all matter with almost no antimatter? Early on, matter and antimatter should have been made equally, and they should have annihilated, leaving just radiation. But we're here, so something tipped the scales, favored matter by just 1 part in a billion. That tiny excess could be from CP violating processes in the early universe. They made a little more matter. After the annihilation, that surplus was left to become everything us. So there's a possibility. The thermodynamic arrow of time, the one that breaks things, might have a microscopic cousin. A fundamental arrow from particle physics, born from CP violation. This particle-level arrow could have been the seed, the nudge that helped set the conditions for our low entropy beginning, which then unleashed the big thermodynamic arrow we feel. That leads to a wilder thought. If our arrow of time is linked to a specific broken symmetry in our region of space, could other regions have different breaks? In a multiverse, could there be places where the symmetries broke differently? Where antimatter dominates or where left and right are flipped? And by CPT symmetry, if charge and parity are opposite there, then time might be reversed relative to us. In such a place, the thermodynamic arrow would point the other way. Beings there would remember what to us is the future. Their cause and effect would run opposite. We could never meet such a region. The boundary between opposite arrows would be chaos, a zone of maximum entropy. No coherent communication possible. But the idea expands the view. It challenges the uniqueness of our time direction. Our flowing present, our sense of history, may not be universal, it could be local. One variation in a richer, multitemporal landscape. We're not just in a universe with one arrow of time. We may be in one bubble of time, inside a far vaster, stranger meta-reality. You have this film strip of reality. It's lying on the table, and the question is the universe just this one frame, the one lit up by the projector right now? Or is it the whole reel, every moment beginning to end already there? That's the old philosophical split. It's been sharpened by physics. On one side you have presentism. Only the present is real, the past is gone. It's memory, the future isn't formed yet. It's possibility that feels true. It matches our experience. Time feels like a river flowing from past to future. It aligns with the arrow of time, with entropy's irreversible march. Each new moment is a novel state, Born from the last, leading to the next. Then on the other side there's eternalism, often called the block universe. In that view, past, present, and future are equally real. They all exist. Just like all points in space exist, you reading this now, your birth in the past, some future version of you, all fixed parts of a four-dimensional structure. Time in this block is like a spatial dimension. The universe isn't becoming, it simply is. That's a radical shift from how we feel. But it finds a powerful friend in Einstein's relativity. Relativity shattered the idea of a universal now. What's present for you depends on your motion, on gravity. Two events simultaneous for one observer can happen at different times for another. There's no privileged present moment sweeping across the cosmos. That deeply challenges presentism. If the present isn't a universal fact, how can it be the only thing that's real? So we're caught between feeling and theory. Our consciousness, our memories, the irreversible increase of entropy, they all scream presentism. We live in the flowing now. Yet the equations of physics, especially relativity, suggest a static, eternal block, where change is an illusion, a kind of cosmic panorama we're moving through. Where does the arrow of time fit in the block universe? If all times exist, why do we experience this relentless direction? Some philosophers and physicists think the arrow is woven into the block itself. The block isn't symmetric. It has a gradient. From the low entropy end we call the past, to the high entropy end we call the future. Our conscious awareness is a process that moves along this gradient, illuminating one slice of the block at a time, like a spotlight scanning a film strip. The flow isn't in the universe, it's in us. We are the travelers through the eternal landscape. This debate is more than academic. It asks what it means to exist. Are we fleeting patterns in a constant state of creation? Or are we timeless world lines, our entire lives laid out like a story already written? It touches free will, destiny, identity. Modern physics doesn't settle it, but it leans. The compatibility of eternalism with relativity, the difficulty of defining a universal present. They give weight to the block universe. Yet the undeniable reality of entropy's arrow, the vividness of becoming, keep presentism alive in our hearts. Maybe the final understanding of time will need a new framework. One that reconciles the static geometry of space-time with the genuine unfolding of events. For now, this philosophical tension is itself a revelation. It shows that to understand time, we have to look inward as much as outward, questioning not just the cosmos, but the nature of our own experience within it. Einstein's universe has elastic time. A clock on a mountain runs faster than one at sea level. Gravity's weaker up there. An astronaut moving near light speed ages slower than her twin back on Earth. That's the twin paradox. It's real. Time stretches or compresses with motion and gravity. It's a fabric, not a fixed metronome. So if time is that malleable, what about its arrow? Does the direction get tangled too? The answer comes from two ideas meeting. Relativity tells us how time bends. Thermodynamics tells us which way it points. And they have to work together. Take the traveling twin. From her view, her ship is still. It's Earth that rockets away and returns, so why is she the one who ends up younger? The answer involves acceleration, turning around, the fact her journey isn't symmetrical. But through all that, her own sense of time's arrow never wavers. She remembers launching, she feels her coffee cool, she sees things move from order to disorder, always toward what she calls the future. Her thermodynamic arrow stays intact. That's the key. The rate of time's passage is relative, but the direction of time's flow is absolute for any observer. Your future is always the direction of increasing entropy in your local patch of the universe. No matter how much your clock is slowed by speed or gravity, you won't see an egg unscramble. You won't get a light signal from a future where entropy is lower. The arrow is woven into your causal horizon, the boundary of events you can influence or observe. But the cosmos as a whole, in an expanding, relativistic universe, can we even define one global arrow of time? It's a deep question. Observers in different gravitational wells moving at different speeds will have their clocks out of sync. Their nows won't line up. And yet, cosmology suggests a kind of cosmic consensus. If you trace back the paths of the galaxies, we all converge to the same hot, dense, low-entropy beginning, the Big Bang. That event gives a reference point, a past for everyone, and from that shared past, the large-scale expansion of space creates a common future direction, the direction galaxies recede, the direction the universe cools. So my now and your now might differ, but our arrows of time are aligned. We all agree the universe was hotter and denser in what we call the past, and is cooler, more diffuse in what we call the future. Relativity and thermodynamics together paint a coherent picture. Time is a flexible, dynamic dimension, but it's not aimless. It's a river with a variable current, sometimes rushing, sometimes creeping, but always flowing downhill. From the improbable heights of cosmic order toward the vast, probable plains of disorder. That union tells us the universe's history isn't just a sequence of events. It's a story written by entropy on the elastic canvas of spacetime. A deck of cards right out of the box. It's in perfect order. Ace, 2, 3 up to king. Hearts, then diamonds, clubs, spades. That exact sequence is one possibility, one arrangement. And if you shuffle it just once, the odds of it going back to that perfect order are so small they're basically zero. It'll fall into one of the random arrangements, because there are far more ways for a deck to be shuffled. Far more ways for it to be disordered. That's the core of it. That's the statistical heart of entropy. Ludwig Boltzmann saw this. He saw that the universe tending toward disorder wasn't some force, it was probability. Played out with unimaginable numbers, a gas filling a room, its molecules aren't being pushed. They're exploring every possible position, every velocity. The state where they're all crammed in a corner, that's like the ordered deck. That's a very small number of specific arrangements. The state where they're spread out evenly, that corresponds to a colossal number of arrangements. The odds guarantee it. The system will be found in that spread-out state, that high probability state. So the flow we see, the arrow of time, it's just the system moving from a less probable arrangement to a more probable one. To make this work, you have to shift your view. You can't track every molecule, so you use a trick. You ignore the microscopic details, the exact position and speed of each particle. You focus on the big picture, the macrostate. Is the gas mostly on the left, or is it spread out? Each macrostate, like evenly spread, can be achieved by a gigantic number of microstates. All the different ways the molecules could be arranged and still look evenly spread to us. Boltzmann's equation captures this. Entropy equals a constant times the logarithm of the number of microstates. It's a measure of how many microscopic possibilities are consistent with what we see. This view transforms the arrow of time. It's not a fundamental mystery anymore. It emerges. It emerges from the collective behavior of countless particles. They follow reversible rules, but they are guided by probability. The reason you never see smoke pour back into a cigarette isn't because physics forbids it. The laws would allow it. If every air molecule and smoke particle conspired in a perfectly coordinated reverse dance, but that dance, that's one specific microstate. One arrangement. The smoky room represents a near infinity of microstates. The system, left to its own wanderings, will almost certainly be found in one of those disordered states. The irreversible world we experience is the statistical certainty of the crowd. So time's arrow isn't a push, it's a drift. A statistical drift from less probable arrangements toward more probable ones. This perspective roots time in something more fundamental. Probability and information. The number of ways a system can be arranged, that's information. And the universe's move toward its most probable states is a story about information being scrambled, mixed, maximized. Our flowing present is the narrative of that journey. It might seem contradictory. A universe moving toward disorder, and yet it creates galaxies. It creates brains. But the idea of disorder, what it means, gets flipped around. In a cosmos governed by gravity, reaching higher entropy isn't always about spreading out. Sometimes it's about clumping together. You look at the early universe. After the Big Bang, it was this smooth, hot particle soup. A uniform sea. By everyday standards, that might seem disordered, but for gravity, that smoothness is a state of very low entropy. It's too simple, too orderly. Gravity wants contrast. It takes the smallest ripples in that fabric and amplifies them. Over billions of years, those ripples become seeds. Matter gathers. It collapses, it heats, it ignites. Stars form, they collect into galaxies. Those galaxies form vast webs and filaments. This immense cosmic structure, this complexity, is actually a state of much higher gravitational entropy. There are far more ways for matter to be arranged in a complex web of clusters and voids than in a perfectly smooth cloud. So the universe's slide toward disorder under gravity built everything. The arrow of time didn't erase structure, it wrote it. And this idea, creation from flow, goes beyond cosmology. Think of a whirlpool in a draining sink. The water is flowing toward disorder down the drain. But in that flow, a stable, organized structure appears. The whirlpool, it's stable but not static. It exists only because energy is moving through. It's a dissipative structure. That's a term from the chemist Ilya Prigogine. Patterns that form and maintain themselves far from equilibrium. They feed on energy flow to sustain their internal order. Your own body is the ultimate example. You are a whirlpool of atoms. You take in concentrated energy from food, from sunlight. You use it to build and repair your ordered form, and you export disorder back into the world. Heat and waste. You are a local island of order, paid for by increasing the disorder around you. Life is a dissipative structure. It's a product of the arrow of time, not an exception. So entropy isn't the enemy of complexity, it's the engine. The drive toward higher entropy creates the gradients. Differences in temperature, in concentration. These power stars, weather systems, ecosystems, mines. It provides the non-equilibrium conditions where self-organization can spark. The arrow of time isn't just a destroyer, erasing what was, it's a sculptor. It carves the intricate shapes of reality from a featureless block of primordial possibility. From the first stars to the first thoughts, the universe's creative journey is written in the language of increasing entropy. This reframes the story. We are not here in spite of time's one-way flow. We are here because of it. The steam engine was the first machine to harness time's arrow. It took the flow of heat from a hot boiler to a cold condenser, and captured a fraction of that flow as work. The entire discipline of thermodynamics came from that, from the gritty challenge of making engines more efficient. Engineers learned you couldn't win. You could only manage the loss. Every power plant, from coal to nuclear, is a carefully orchestrated dance with entropy. Its design focuses on creating the steepest possible temperature gradient to maximize work, while ensuring waste heat is carried away. The goal is to guide the inevitable increase in entropy in a direction that powers our cities. This isn't just engineering, it's applied philosophy. It's the deliberate steering of time's one-way flow for human benefit. Flip the arrow and you get refrigeration. A refrigerator fights the natural flow of heat. It pushes heat from a cold interior to a warmer room. But to do this, it must pay a price. It consumes work. And in the process, it releases even more heat out the back. The local order inside your fridge is purchased by creating greater disorder in your kitchen. This is the second law in action, a transaction that cannot be avoided. The efficiency of every air conditioner, every heat pump, is fundamentally limited by this thermodynamic truth. Our entire modern comfort depends on our ability to intelligently manipulate these flows, to temporarily reverse time's arrow in a small, insulated box, while acknowledging its dominant direction everywhere else. This practical understanding extends far beyond heat and engines. Maxwell's demon, that clever thought experiment, seemed to cheat the second law using information. Today, that isn't just a puzzle. It's a blueprint. In nanotechnology, where devices are so small they're buffeted by thermal noise, the line between information and energy blurs. Designing a molecular switch or a nanoscale sensor requires thinking like the demon. It forces engineers to account for the thermodynamic cost, the cost of measurement and erasure at the scale of individual particles. This is where information theory and thermodynamics fuse. Landauer's principle made it concrete. Erasing a single bit of information in a computer must release a tiny amount of heat. It's a fundamental tax on forgetting. This principle sets the ultimate limit for computing. As we pack more transistors onto chips, pushing towards the atomic scale, we're not just battling electrical resistance. We're confronting the thermodynamics of information itself. The heat generated by a processor isn't just an engineering nuisance. It's the physical manifestation of countless logical operations, each one irreversibly processing and discarding data. The quest for energy-efficient computing, for green data centers, is a direct application of understanding time's arrow. It's about minimizing the entropy we generate with every calculation, because that entropy is waste heat. The future of artificial intelligence and quantum computing depends on mastering this relationship, on building machines that compute closer to the thermodynamic limits of efficiency. So this abstract concept, born from pondering broken vases and cosmic beginnings, is the silent partner in every technological leap. It guides how we generate power, how we cool our homes, how we design the next generation of computers. Our policies on energy and sustainability are, at their core, discussions about managing entropy on a planetary scale. We are learning to work with time's arrow, not against it. To build a future, we must first understand the irreversible flow that makes a future possible. And this understanding forces us to look ahead, to a horizon defined not by machines, but by the mind itself. What does it mean for consciousness, for our sense of self, if our thoughts are also physical processes governed by this same relentless law? The spiral jetty sits out in the Great Salt Lake. It's this coil of black basalt, just reaching into the water. Robert Smithson built it in 1970. It's an earthwork, a monument to time's arrow, and since then, the lake's water has gone up and down. It's left the rocks crusted with white salt, so the work changes, it decays. It's embracing its own transformation, a physical form of entropy right there in the landscape. Art has always been this conversation with time, a way to hold a moment, to resist the scatter or to accept it. And that creative impulse, it's like our cultural echo of a cosmic law. When a poet writes about time present and time past, or a filmmaker bends a story into a circle, they're mapping the same terrain a physicist charts with equations. They're grappling with the human condition inside a one-way flow. Take the opening of T.S. Eliot's Burnt Norton. Time present and time past are both perhaps present in time future. That line feels like a paradox. It suggests all moments might coexist. But the poem itself is filled with this ache for what's lost. A rose garden that's always just out of reach. That tension, that's the artistic heart of it. Our minds can conceive of eternity, of cycles, of timelessness. But our bodies, our hearts, they live in sequence. We feel the before and the after. And art gives form to that feeling. An epic poem tries to preserve a hero's name against the erosion of centuries. A portrait captures a face that will age. A symphony moves from a theme through development to a resolution. It's a miniature journey, a beginning, a middle, and end. These structures are metaphors for life itself, for our journey from order to disorder. Some artists make entropy their medium. Composers have written scores where musicians play sections in a random order, letting the piece decay into a different form each time it's performed. Sculptors use materials that rust, that melt, that get reclaimed by nature. These works don't fight time, they collaborate with it. They make the invisible arrow visible. They show that beauty isn't separate from transience. It's often defined by it. There's the Japanese aesthetic of wabi-sabi. It finds beauty in imperfection, in impermanence, in the patina of age, a cracked teacup mended with gold. It's a philosophy that honors the marks of time's passage, seeing in them a deeper, more authentic kind of order. Modern storytelling often wrestles with time's nonlinear nature. It's a reflection of our scientific understanding. The film Arrival presents aliens who perceive time not as a line, but as a complete circle. For them, all events exist at once, and the human linguist's struggle to learn their language becomes a struggle to perceive reality in this new way. To experience her own life as a whole. The story is powerful because it mirrors our own deepest questions. Is our linear experience an illusion? Is grief for what is lost, or joy for what is to come? Are they based on a limited view? These narratives don't provide answers. They expand the question. They let us feel the mystery. This cultural reflection connects the cosmic to the intimately human. Our drive to create, to build, to leave a mark. It's fundamentally a response to entropy. We plant gardens knowing they'll grow wild. We write books knowing pages will turn to dust. We raise families, build communities, launch ideas into the future. Each act is a local rebellion against the scatter, a temporary eddy of order in the universal flow. But in the grandest view, these acts of creation are also part of the flow. They are dissipative structures, sustained by energy and destined, ultimately, to contribute to the wider dispersion. This isn't a bleak thought. It gives our struggles meaning. The symphony fades into silence, but the experience of it, the memory, becomes part of the complex history of the universe. Our art, our stories, our monuments, even the ones that decay, they are the universe becoming aware of its own irreversible journey. They're the notes it sings to itself about time. And in that song, we find not just an understanding of a physical law, but a reflection on what it means to be a conscious part of this vast, unfolding process. Laboratories have become quiet places to study time. Scientists build devices now, tiny, sensitive, that can watch thermodynamics play out for a single particle. These are quantum thermodynamics experiments. They test the foundations. They take a lone atom or a microscopic resonator, put it into a superposition of states, simultaneously warmer and cooler, and they watch how it interacts with its environment. The goal is to see in real time how quantum coherence decays, how it becomes classical certainty, how the irreversible arrow emerges from reversible laws. Each precise measurement at this scale, measuring heat flow, work extraction, it's a direct probe. A probe into the connection between information, energy, and time's direction. In the digital realm, other frontiers are being mapped. Researchers use supercomputers. They simulate information falling into a virtual black hole. These aren't full models of quantum gravity. They're sophisticated thought experiments made real. They apply quantum information theory to the geometry of spacetime. They test ideas like holography. Can the information of a three-dimensional star be perfectly encoded on the two-dimensional surface of the black hole it creates? The simulations look for clues in the patterns of entanglement. They search for the signature of information preservation. In the Hawking radiation, every iteration brings us slightly closer. Closer to resolving the paradox, the one that threatens our understanding of cause and effect. Our largest telescopes are also time machines. They peer back to the universe's first moments. Observations of the cosmic microwave background with ever greater precision map the faintest ripples in the primordial plasma. These are the imprints of quantum fluctuations from the inflationary epoch, stretched across the sky. By studying their pattern, cosmologists hope to infer the conditions, the physical conditions that set our low entropy starting point. Was it a unique event? Or one of many in a larger multiverse? Each new dataset, from observatories on the ground and in space, it constrains the theories. It slowly narrows down the possibilities. For how time got its arrow. From all this, new theoretical frameworks are emerging. One is quantum causality. It suggests the sequence of cause and effect might not be fixed. It might emerge from more fundamental quantum relations. In this view, the temporal order of events could be indefinite, like a particle's position, until a process of decoherence picks out a particular history. It's a radical reimagining of time's flow at its root. Another speculative idea is entropic gravity. It proposes that gravity isn't a fundamental force. It's an entropic effect, a consequence of the universe's tendency to maximize entropy, like a stretched rubber band snapping back. It's controversial, but it represents a bold attempt to derive the large-scale structure of spacetime from thermodynamic principles. This is no longer just a puzzle for physicists. The mystery of time's arrow has become interdisciplinary. Computer scientists design algorithms inspired by thermodynamic efficiency. Philosophers of science analyze the logical structure of explanations. For the past hypothesis, information theorists provide the mathematical language to describe complexity and causality. Biologists examine how living systems harness energy flows. From cells to ecosystems, how they maintain their ordered state against the entropic tide. The conversation is converging from all these angles. Each field illuminates a different facet of the same profound diamond. All this work circles back to that foundational question: will we ever find a fundamental reason for the past hypothesis? A law that explains why the universe began in such an improbable state? A state of low entropy? Or is it just a brute fact, the ultimate initial condition with no deeper explanation? The answer will determine something: whether time's arrow is an inevitable feature of any coherent cosmos, or a contingent accident of our particular cosmic story. This is the active frontier. The mystery of time isn't a solved problem in a textbook. It's a living quest. It invites the next physicist, the next philosopher, the next curious mind to look at a broken vase, or a spreading cloud of steam, or the silent expanse of the night sky, and ask why. Why does the story only run one way? The search for that answer remains one of science's most profound journeys. It reminds us that some of the deepest truths about reality are written in the simplest experiences. In change and loss and forward motion, all the arrows point the same direction: the thermodynamic arrow moving from order to disorder, the cosmological arrow of an expanding universe, and the psychological arrow of memory and anticipation. Even the quantum arrow from possibility to fact. They're not separate mysteries. They're currents in the same river, all flowing downstream from one source. That source is the moment of incredibly low entropy we call the Big Bang. That starting condition was the wound spring. It gave the universe a direction to unwind. The expansion of space created the arena. Gravity could build structure, increasing gravitational entropy. That process formed stars and planets, environments where thermodynamic gradients could exist. On at least one planet, those gradients fueled chemical reactions complex enough to become self-sustaining, to become life. Nervous systems evolved that could model the world, forming memories of a lower entropy past to anticipate a higher entropy future. Our consciousness, our sense of time flowing, is a consequence of that same thermodynamic drift. At the quantum level, processes like decoherence are irreversible. They generate entropy. They create a record of the past, aligning the quantum arrow with all the others. It's a cascade. From the smooth simplicity of the primordial fireball to the intricate, remembering mind contemplating it. Every arrow is a chapter in the same story. The story of a universe exploring its possible states, moving from a rare, ordered beginning toward a probable, disordered future. Imagine a great, multi-layered river. On the surface, the psychological current, your thoughts and memories flowing. Beneath that, the strong thermodynamic current, the pull toward disorder. Deeper still, the cosmological current, the stretching of space itself. And at the bottom, the quantum current, the fundamental hum of reality settling into facts. They are distinct, but they move in concert, carving the channel of time through the landscape of reality. This alignment isn't a coincidence. It's the signature of our cosmic history. In a different universe with a different beginning, These arrows might point in opposing directions, or not exist at all. We find ourselves in a universe where they line up, creating a consistent, unambiguous past and future. This is why we can trust our memories. This is why cause precedes effect. This synthesis offers an elegance. It shows how disparate facets of physics, from the cosmic to the cognitive, conspire to produce the unified experience we all share. The ticking of a clock, the aging of a face, the expansion of the cosmos. They're all manifestations of the same underlying drift. The final question becomes one of unification. Could a theory of everything, a complete theory of quantum gravity, explain why these arrows are necessarily aligned? Could it derive the low entropy Big Bang not as a mysterious starting point, but as the only logical outcome of deeper laws? Some physicists hope so. They seek a framework where time's arrow is not an initial condition tacked on, but an emergent property, a natural consequence of the universe coming into being. We're not there yet, but the journey to understand time has given us a map. It shows how the personal, the cosmic, and the fundamental are woven together into the fabric of now. We live in the flow, and we are the flow. Understanding that might be the most profound closure of all. It started with a vase, broken on the floor, just a thing that fell apart. That question, why things fall apart, it leads you back to the steam engines, the 19th century. That's where they first saw the law that governs all change. Then Ludwig Boltzmann, he saw disorder as probability, a numbers game with atoms that was the insight. It revealed the arrow, the thermodynamic arrow. The one all the others follow. You follow it outward to the beginning of everything, smooth, hot, the low entropy Big Bang that wound the spring and then gravity. It reverses the meaning of disorder. It builds galaxies from that smoothness, stars, all while entropy increases. Then you confront the black holes, the ultimate sinks for entropy. And quantum mechanics. It weaves irreversibility right into the fabric. At the most fundamental level, you trace the arrow inward too, into the mind. Where memory is a thermodynamic process, consciousness into life itself. Life sustains its order by speeding the flow, speeding the universe toward disorder. And you look to the farthest future, the heat death, where the arrow might fade into a silent equilibrium. Timeless, through all of that, one concept is the constant. The hidden force, entropy, the implications touch everything, our ability to remember yesterday but not tomorrow, the flow of our conscious lives. That's a gift of the second law. The entire evolution of the cosmos, from a featureless fireball to a tapestry of galaxies, that's the story of entropy increasing, the reliability of cause and effect. The reason a dropped glass shatters and doesn't reassemble, that's rooted in the statistical drift, from order to disorder. All of it hinges on one special fact. Our universe began in a state of incredibly low entropy. That initial condition, it's the foundation, the reason there's a past distinct from a future. Stephen Hawking put it elegantly. He said the increase of disorder, of entropy, is what distinguishes the past from the future. It gives a direction to time. That direction isn't an illusion, it's the deepest rhythm. So an ice cube melting in your drink, a tree growing from a seed, recalling a memory, you're seeing more than a process. You're seeing the cosmic dance of entropy. You're watching time itself unfold.